Okay. Does it work? It works. Okay, even if it is a school on phonons, my emission of phonons is quite small, so I need a microphone, otherwise you won't hear me. Okay, good morning to everybody, and thanks to the organizer for having invited me and to open this very interesting workshop. And I'm Paolo Giannozzi. And I've already lost the microphone. Here, you mean? No, better here. Okay, and I'm going from the University of Udine. If you don't know where it is, it's not far from here, 60, 70 kilometers. And I'm going to give a brief, but actually not so brief, introduction to density functional theory and also to the plane wave pseudopotential method, which is what we are going to use in most, during this workshop. I have a lot of slides, so I'm not going to try to fit everything into this hour. If something is left out, we'll see it later in the afternoon. So first principle, where do we start from? We start from, at least ideally, from the Schrödinger equation for a system of nuclei and electrons in reciprocal interactions. And we write this quite complex problem to solve. Then of course, we move to time-independent, the solution of time-independent equations, and then we have to disentangle in some way the motion of nuclei and of electrons. Well, sometimes you shouldn't, but in most cases, we start from the so-called adiabatic approximation. So we start from the assumption that electrons follow adiabatically the motion of nuclei. So mathematically, what you do is that you write these all-electron, electron and nuclear wave function into a product of nuclear wave functions time electron wave function depending upon the nuclear position. Then you put inside the equation, and by neglecting some terms, in particular the gradient of the electronic part times the gradient of the nuclear part with respect to nuclear positions, then you find that you can write the electronic term, an electronic equation like this, in which the potential depends upon the position of nuclei. And then what you find here for the energy depends also upon the nuclei. And this is what defines the so-called potential energy surface. So the energy as a function of the nuclei, energy that includes nuclear repulsion energy and nuclear electron attraction energy, and also electronic energy. And so the object of our desire is this potential energy surface, this energy as a function of nuclear position. And this is also what determines the motion of nuclei. So we can disentangle in this way the motion of electrons from the motion of nuclei. Once this is done, we have still to solve an electronic problem, which is a complex many-body problem. And one of the typical ways to solve the electronic problem is to resort to the so-called density functional theory. Density functional theory is actually derives from an old idea which dates back to the 30s. So the idea of considering the charge density instead of of the wave function as the basic variable. So try to solve for the charge density instead of solving for the all electron ops. No, okay, this one for the all electron wave function. So this is the correct many-body definition of the charge density. Of course, once you have a potential, so you have to solve the original problem depends upon this potential that is written here. So once you have this potential as a function of a nuclear position that you assume to be fixed for the time being, you have automatically the solution, well, not automatically, but in principle, you have the solution and a corresponding the wave function, I mean, and a corresponding charge density. So you have a relation between potential on one side and the charge density of the ground state. I'm always talking about the ground state, electronic ground state here on the other side. And it's less obvious that you have also the opposite relation. So given a charge density, a ground state charge density, you have a unique potential that has that charge density as ground state charge density. But this can be demonstrated, and mathematically it's even quite simple to show this, and it goes under the name of Hohenberg and Kohn theorem. So, but actually, what one demonstrated is that there are no two different potential corresponding to the same, having the same charge density as ground state charge density, or that if they are not the same, they differ by a constant. So a constant does nothing, but the difference is just a constant. Now, this has some far-reaching consequences. For instance, you may easily show that you can write the energy, the electronic energy, as a functional. So a functional of the charge density. So a functional is a sort of generalization of the idea of a function. So a function associates a value to another value. A functional associates a function to a value. So a function of the charge density that can be written in this way as an interaction with the external potential, the potential of the nuclei over electrons, plus a universal functional that doesn't contain the potential, the external potential, this one, and that is universal, so it's the same for whatever system. And another consequence is that the ground state charge density, subject to the constraint of having the correct number of electrons, of course. So if you have a capital N electrons, then you have the constraint that the integral of this charge density has to give N, capital N. Under this constraint, the charge density minimizes, the ground state charge density minimizes the energy. So this functional is minimized by the ground state charge density. And this gives you a way, at least in principle, to solve the problem in terms of the charge density, which is a three-dimensional function, much simpler than the dimensional function of the position, much simpler than the wave function, which is instead a complex many-body object. Of course, this would work great if we knew how this functional, this universal functional is done, how it is, its properties. If we knew a way to write it explicitly, but this is of course not possible. We just know that it exists. Now, how can we manage? How can we use in practice this theorem? Now, the first answer came from Konesham 1 year later, who introduced a set of auxiliary one-electron objects called Konsham orbitals, defined in such a way that they yield the same charge density as for the true system. So you have the charge density of the true system. You introduce a number of one-electron Konsham orbitals such that for non-interacting electrons, so it's a fictitious system of non-interacting electrons, and the charge density, the true charge density is given as the sum of the square of the non-interacting electrons, and this would be, this is actually the charge density for a system of non-interacting electrons. It's just the sum over the squares of the wave function of the single wave function of the wave function of the single electron. Under the constraint, of course, of orthonormality. This guarantees of orthonormality of the Konsham orbitals. This guarantees the correct normalization if you have the proper number of these Konsham orbitals. So you have, assuming neglecting spin, if you have capital N electrons, then you need capital N one electron Konsham orbitals. Now we rewrite the energy functionals, which is still unknown, but we rewrite the energy functional by extracting the most important parts from these functions. So we extract what we know, what we manage, what we can easily write. So in particular, we extract what? The energy, the kinetic energy of the non-interacting electrons, which is not the kinetic energy, the true kinetic energy of the system of electrons. It's close, but it's not exactly the same. Then we extract the average electrostatic interaction. So the Hartree term is nothing but the interaction, the electrostatic interaction between clouds of charges with charge density N of R. Then we introduce the interaction with the external potential. Here it's assumed that the external potential is a local potential. And then we leave everything else here inside. So this is the expression of the kinetic energy for non-interacting electrons. It's a usual form of the kinetic energy. And this is the form of the so-called Hartree energy. It's an electrostatic interaction. This, of course, we don't know. Then at this point, we minimize the energy. So we say, okay, what are the Konsham orbitals that give the correct ground state, give the correct ground state, always with the constant that they have to give the charge density of the system of real electrons, and with the constraint that orbitals have to be orthonormal actually. Then, in this way, by minimizing the energy, one finds the effective potential acting on electrons, on these non-interacting electrons, this auxiliary system of non-interacting electrons, and this is the form. So it's a traditional Hamiltonian with an effective potential and a kinetic part. And so we have to solve these equations called the Konsham equations. And okay, this is clearly the external potential, the potential of the nuclei. This is the potential, the electrostatic potential, and it's also related to the functional derivative of the electrostatic energy. So it has this form, it is a potential, the potential of a cloud of charge. And this we still don't know, but we write formally as the functional derivative of the charge density of the exchange correlation functional with respect to the charge density. Notice that the charge density is here. It's somewhere here. So, and it depends upon the Kohn-Sham orbitals. So it's the problem is self-consistent. So the solution, the equation depends upon the solution. So you have to verify that the solutions are compatible with the potential you have assumed. And this is an alternative way to rewrite this energy as a sum of our Kohn-Sham eigenvalues. Those quantities here is called Kohn-Sham energies or Kohn-Sham eigenvalues. You see that it's a sum of occupied orbitals, so the orbitals that contribute to the charge density, minus double counting terms like this one for electrostatic energy. So it has to be subtracted out because it's present twice here, minus this term that appears here, plus the true, so to speak, energy, exchange correlation energy. In Hartree-Fock, you have something similar, but this term and this term are the same. Well, they're not the same. This is 2 times this one. In density functional theory, this is not true. So this term and this term are not the same. They are different objects. Okay, so still we haven't solved the problem, what is this exchange correlation energy. And so we have to figure out some approximation, some viable approximation for this exchange correlation functional. And the first historical proposal, well, at least maybe not the very first, but the first modern, so to speak, proposal for an approximation is called local density approximation. So in the local density approximation, you write the exchange correlation energy this way by, let's say, as a density of, as an exchange correlation energy density times the charge density. And this energy correlation energy density is obtained from the results for the homogeneous electron gas. So the homogeneous electron gas is a model system in which you have a constant density. So you can compute for that system this quantity as a function of the homogeneous charge density. Then locally, in each point, you assume that the exchange correlation energy density is the same as you would have in the homogeneous electron gas for n uniform density equal to n of r, the local density. So that's the origin of this local density name. There are techniques that allow to solve practically exactly the homogeneous electron gas, particular quantum Monte Carlo technique. So this function here, this function epsilon xc of n0, let's say, is known as a function of n0. Actually, one uses more often than not, one uses not S0, but the Rs, that is the parameter that is used in the theory of metals. So the volume of a sphere of radius Rs is equal to the average volume per electron. Anyway, there are analytical formula quite simple that you can fit to Monte Carlo results for the electron gas, and so you can obtain this approximation. So apparently, one might say, okay, that's nice for systems in which the charge density varies slowly. So systems that are almost homogeneous. So one might say, okay, metals have a relatively homogeneous charge density, but what about all other cases like atoms, molecules, or cases in which the charge density is far from homogeneous. Actually, this works better than one might expect. But still, one would like to take into account the lack of homogeneity of the charge density. So the fact that the charge density is a function that varies with the position. So one might want to take into account the fact that there is a gradient of local gradient of the charge density, and this should be taken also into account. It's not that simple actually to write a functional of the charge density and of its gradient. So the first attempt failed miserably. You have to consider that there are a number of some rules and of results for the exact functional that have to be kept. Otherwise, the gradient corrected functionals are worse than the gradient uncorrected ones. But finally, some generalized gradient approximation, so called, have been proposed, and they work quite nicely. Of course, they depend upon not the gradient, but the modulus of the gradient of the charge density. But in principle, you can generalize this form of the extrinsic correlation energy in this way, in which this energy density depends upon the local density and the local gradient, the modulus of the local gradients. Now, there are many possible functionals that one can define in these two classes. So these are the two, among the simple functionals, these are the two simplest classes. Local density approximation, so a function of the local density, and generalized gradient approximation, a function of the local density and of the local gradients. There are many different functionals that can be written in this way. They all give, those of the same class tend to give all very similar results, because they are actually very similar if you look at how they are defined, and you discover that they are very similar in the region of charge density that is interesting for typical condensed matter systems. So they look all different, but in the end they are almost equal. But still, there are many different flavors. And some flavors are slightly better for some characteristic, and some are better for others. Yes, please?
Should we introduce some the conservation law to the local gradient?
Some?
Conservation law, if we introduce some local gradient of the
There are some rules that have to be enforced. Yes, that to be respected. I don't know very well how these objects are derived. That there are some rules that have to be enforced. Otherwise, you get funny results, not so good results. Conservation law, you mean? No, but actually those GGAs are always written as function of the charge density and of not of the gradient, but of the gradient to the power 4 to 4 divided by 3 by divided the charge density. They are functions of not direct of the gradient, but of a combination of the gradient and of the charge density. Anyway, they are well-defined functions. Yes?
It is something quite basic that I don't understand here with LDA, GGA. In the LDA, you are saying that you're looking at the local density associated with extent correlation value from the homogeneous electron gas. And so, why does it matter that one system has, you know, a charge density that is very wildly and another one doesn't, when in fact, the picture that I have is that although it is varying, at each point you're picking the density that corresponds to. So you must then incorporate the variation.
Yes and no, because the result would be exact only for homogeneous charge density. So the result for homogeneous charge density is exact. For non-homogeneous charge density, well, it's an approximation. It's an assumption. You are assuming that the exchange correlation energy is done like that. But the functional is an object that is more complex than a simple function of the local value. So functional is an object that takes a function and somehow produces a value. This is something, if you look at the exchange correlation potential in this approximation, then you see that it is a function of the local charge density, really a function, not a functional. So you are restricting the field of your possible solutions. Okay, this is the basic. So LDA and GGA are, let's say, the basic assumptions, the basic approximations, which work quite nicely for a variety of problems. They have some well-known shortcomings, so they may not be the best solution for an acceptable solution for all cases. You may have noticed that there is nothing like looking like a spin in this theory until now. In fact, the original density functional theory works for a strange object, so it works for spinless fermions, which are of course a contradiction. But the extension to fermions with spin has been derived, and what one finds is that the exchange correlation functional is a functional of the charge density. Well, in the simplest case, so in which you choose a single quantization axis and you assume that your states are either spin up or spin down. In that case, you have spin up and spin down charge density, and you can write an exchange correlation functional as a functional of spin up and spin down charge densities. Actually, more often than not, these exchange correlation energies are written in terms of the total charge density and the polarization, the local polarization, so the difference between spin up and spin down at a given point. Notice that this treatment of spin, for historical reasons, is called local spin density approximation. So one might think it works only for local density, so it's an extension of local density, but actually it works also for GGA, so it's an historical name. So what is LSDA actually means is that we assume a single quantization axis, and we assume to have all states or Cauchy states with spin up or with spin down. There is also generalization to the general case in which you don't have a single quantization axis, and in which you write a functional. Well, you consider your Cauchy orbitals are not simple functions, but spinos, so functions with a spin up and spin down part. And you write the exchange correlation functional as a functional of the total charge density plus a term that depends upon the local magnetization, which can be a vector, which can change in the system. While in local speed density, you have magnetization up or down. Here, in the general case, it's called non-collinear case. In non-collinear magnetism, you have a magnetization that has a direction, a local direction that changes, that may change as a function of the position. There are cases in which this is important, in which the local spin density approach is not sufficient because the magnetization has different positions, different directions in different points. Notice that I have here introduced silently, not so silent because it's written explicitly here, another extension of DFT to fractional occupations. This is important for metals. Until now, implicitly, I have assumed that you have either occupied Kohn-Sham orbitals or empty Kohn-Sham orbitals that don't contribute to the charge density. But you may also consider the case in which you have a fractional occupancy, and this is important for metals. So you add, in this case, this occupancy, which of course range from 0 to 1. Okay, all this actually works quite nicely, sort of rather surprisingly, also for atoms. So here, those slides I borrowed from Stefano De Gironcoli. If you look at, if you can read numbers, not sure you can, but if you can, you notice that those numbers, both LDA and GGA numbers for the energy, this is the absolute energy of an atom. So it's something that you measure by taking an atom and removing one after the other electrons. So you sum the ionization potentials until the last one, and then you have the total energy of atoms. And this quantity, this is absolute quantity, is absolute energy that is quite well reproduced in LDA and GGA. LDA tend to underestimate the stability of atoms, while GGA is better. Both have a funny problem, which is quite well known. So negative ions are not stable. So negative ions in this framework don't exist. Of course, this is not exactly what one observes. For small molecules, one finds that binding energies and binding and bond lengths are also quite reasonable. LDA here shows a clear problem is that the binding energy tends to be overestimated. This is typical for LDA. It overestimates the binding. While GGA is much better in this respect. And if one looks at simple solids, one finds also a reasonable pattern of results, and quite consistently, LDA tends to overbind again. So the distance, the equilibrium lattice parameters are typically smaller than in LDA than the true ones. And GGA is somewhat tend to slightly overestimate those lattice parameters. And as a consequence, LDA gives too high bulk moduli, so second derivative of the energy, while GGA tends to give somewhat softer materials. So materials in LDA are somewhat compressed and stiffer. Materials in GGA are somewhat slightly expanded and softer. And even for nastier objects like oxides, results are not so bad. Here actually it's a little bit more, this is trickier actually. So results of LDA of GGA may look reasonable, but if one looks more careful, then one sees a number of problems. Okay, what are these problems? These problems of LDA and GGA are invariably related to two characteristics of the true exchange correlation function, which we still don't know, but we know a few things about it. In particular, we know two things that have to be true necessarily. One is that if you have a single electron, of course, if you look back at the formalism, you have a single electron, you have no exchange correlation potential. Or more exactly, you have an exchange correlation potential that must compensate the Hartree term, because the electron cannot interact with itself. So this interaction of an electron with itself is called self-interaction. In Hartree-Fock, if you perform a Hartree-Fock calculation for one electron, then you have exact removal of exact cancellation of the self-interaction by construction. This is not, unfortunately, true for all approximate density functionals. So invariably, you have that one electron interacts with itself. Now, the interaction is small, but it's sufficient to make up for most of the trouble of DFT. So in particular, what I was mentioning before about the negative ions that are not stable is a consequence of self-interaction. And many other cases, many other problems are a consequence of self-interaction. And another funny characteristic of the density functional is that if you consider it as a function of the number of electrons, so if you consider it as assume that the charge density is a continuous function, and the total charge density is a continuous function of the number of electrons, so the number becomes a real variable, you will have something that depends upon the number of electrons, but this something, this energy, has to have a cusp corresponding to integer number of electrons. This is because if you add an electron or if you subtract an electron, the energies involved are different. Now, this is not something, both characteristics, both aspects are not obvious to enforce with a simple form of the exchange correlation function. Actually, it's impossible to write a function, a simple function of the charge density of the gradient or something like this that can enforce, can respect both of these aspects. So what are the what can you do with basic simple LDA and GGA? Well, you can do calculations in condensed matter systems of all kinds because it's simple. So it's a simple. These are simple approximations. So you can do quite complex cases with plain DFT, LDA, GGA. And the results are actually good, especially for weakly correlated semiconductors, but also for more difficult materials like the oxide I've shown before. Structural properties come out quite well, with a quite satisfactory accuracy. But there are known problems, and one of the known problems is the infamous band gap problem. So in principle, the difference between, you would like to have the difference between the highest occupied valence orbital and the lowest unoccupied conduction orbital, or HOMO-LUMO in quantum chemistry dialect. You would have this difference of the eigenvalues to be your band gap. It is not. It is wildly underestimated. Even you may have cases in which your semiconductor turns into a metal. Germanium, for instance, is one of those borderline cases in which it's a semiconductor with a relatively small gap, but not as small. In fact, once upon a time, there were first transistors were based on germanium. I'm old enough to remember when the germanium transistors were still existing and used. But germanium, LDA germanium, the sort of semi-metal. I've mentioned before strongly correlated materials, so materials with strongly localized electronic states like 3D in transition metals. So these are the electronic states, atomic electronic states that tend to stay atomic-like even in condensed matter systems, and that are responsible for magnetism, for instance. For these materials, the incorrect calculation of self-interaction is a problem because you have strongly localized electrons, and so you have a significant self-interaction. Finally, if you look at how a GGA LDA function is defined, it is defined as a function of the local potential and gradient, of the local charge density and gradient, sorry, which means that if you have two systems that do not overlap, the exchange correlation energy is simply the sum. No overlap, no interaction. But van der Waals interactions don't depend upon overlap. They are interactions between fluctuating dipoles, which in principle are non-local. And so there is no way to account for van der Waals interactions in using this so-called semi-local approximation. They're called semi-local because, basically, they are local approximation of the charge density using the local value of the charge density and of the gradients. Yes? Yes?
Did you say that because you consider this
Local
local density?
density or gradient, yeah, and gradient, yes. Mm-hmm.
But I thought we also we still solve for Coulomb equation. And Coulomb interactions are non-local.
Well, yes, but yes, of course, the Coulomb interactions are accounted for exactly. So one of our interactions, yes, they are.
And Coulomb interactions should be able to capture like dipole.
So,
So you're saying that it has more to do with the dynamic or like fluctuation.
yeah, it's a fluctuating dipole interaction. Of course, if you have a fixed dipole interaction like in water molecules, this is water. Water has a dipole. Water molecules have a dipole, and the interaction of this dipole is perfectly reproduced, is perfectly accounted for by the Hartree term. Sure. But van der Waals is something more subtle. It's in perturbation theory, you can see that you can derive it from second order perturbation theory. Okay, you may say, okay, I don't give a damn about Vanderbulge interactions, but still there are a number of cases in which it's important instead. So what can we invent in order, what have people invented in order to deal with those shortcomings of, of density functional theory? Well, first approximation that somebody doesn't like, but that works quite nicely and it's quite cheap for, strongly correlated cases, so materials with strongly localized atomic orbitals is called DFT plus U. In DFT plus U, you add a correlation term of Hubbard time that has, in the simplified, in the most simple case, this form, where this N is a matrix of the occupancies. You project your Kohn-Sham orbitals onto a selected manifold of atomic-like states. So, for instance, 3D states for iron, and you have this term, and this term has the important characteristics to distinguish between integer numbers of electrons and non-integer numbers. So it corrects in some way for the lack of discontinuity when you cross an integer number as a function of when the charge density crosses, the total charge density crosses an integer number. So this cartoon is by Stefano De Gironcoli here, and it's meant to represent a localized orbital in a sea of delocalized bands as a function of the occupancy of the localized orbitals. And so what you get from plane LDA or GGA is this continuous curve as a function of the occupancy of this state, while the corrected functional has this piecewise linear behavior, which is the correct behavior. As a consequence, here you get an integer, you tend to get integer occupancies, which is what you actually observe, while with LDA you tend to get mixed occupancies that are unphysical. So what happens sometimes is that you get good results with GGA or LDA because you happen to get the correct occupancy of localized orbitals, but it's sometimes it happens and sometimes it doesn't. So it's not something you can rely on it. A further advanced functional that is quite recent, actually. Well, not that recent. Actually, it exists since a few years, but it has always been difficult to use. The so-called meta-GGA. Meta-GGA are what? They are the next step in the design of functional. So LDA, charge density, local charge density only. GGA, local charge density and local gradient. Meta-GGA, meta, this is beyond. Then you add the dependency upon this quantity here. Oof. This quantity here that is a sort, well, no, it's not nabla square, it's nabla. Well, I'm not sure this is correctly defined. I think it's nabla, it's not nabla square, sorry. And this quantity you can write, you can use to write a functional that depends upon the charge density, the gradient of the charge density, and this so-called kinetic energy density. It's definitely more complex than GGA to use, much more complex, because when you compute the functional derivative of the energy, of the exchange correlation energy, you have a term coming from here that changes your Hamiltonian. So it's not simply V of R, a potential. For GGA, the exchange correlation potential is a local potential, so it's in a simple object. In beta GGA, you have the simple object plus other objects that change the Hamiltonian. So It's relatively complex to use, and it's numerically not easy. These objects are quite nasty numerically. But recent meta-GGA functionals seem to work very well. And in particular, this scan is the latest trend in access correlation functional. Is this one, meta-GGA, notably this scan functional, which seems to give very accurate results, even if it's not very cheap, but it seems to work very nicely. Another approach that works quite nicely, but it's also a little bit computationally heavy, is called hybrid functionals. Hybrid functionals derive from quantum chemistry. So in the quantum chemistry world, the first reaction to DFT was, it doesn't work. For some good reasons, because it depends upon which kind of accuracy you are used to. But later it was realized that by mixing some exchange, some exact exchange, that is some Hartree-Fock exchange with DFT, so by mixing a little bit of Hartree-Fock with DFT, you could get some very accurate results. Now, what is the problem here? Well, the problem is that you have a lot of different density functionals available, and then you have even a further parameter. So the problem number one is that you have an additional parameter. So the admixture, how much exact exchange you add to your DFT functional. And the second problem is that if you work with plane waves, this is horribly slow. This part here, it has this form, is horribly slow. It scales as you have to make products of all states, of all occupied states, of all pairs of occupied states, so it's very slow. There are some recent developments that are very, very promising to speed up the calculation, the usage of hybrid functional with DFT. Okay, coming to the problem of Vanderbulge. There are various approaches for this. One approach is, but from first principle, you say, okay, I write down a functional that may account for non-local interactions like Vanderbulge. And in general, you have to write something that has this form. This is the most general non-local form, well, not the most general, but a general form for a possible form for a non-local object. So you have the charge density as a function of R, the charge density as a function of R prime, and the kernel. And this kernel is also a function of the charge density, of the gradient of the charge density, and of the difference between R and R prime. So it's a rather complicated object that also exists since years, but it was basically unusable because too expensive. But there have been some algorithmical improvements, in particular the Sollers technique, that have allowed to write those non-local functionals in a way that is reasonably cheap from a computational point of view. So this is one possibility, non-local functional. They work quite nicely. They tend to overestimate binding a little bit. Again, another problem is that you have a large choice. There is only one part. So you have the non-local term plus the local term, plus the exchange correlation P, some GGA. So you have an ample choice between different functionals. The alternative is to add Vanderbulge interaction manually, so to speak. So you have your GGA that doesn't account for the Vanderbulge interaction, but you have you know how the Vanderbulge interaction works. It's something that more or less the main contribution, you may have also other terms, but the main contribution is this 1 over R6. And this object here is related to the atomic polarizability. So one may try to fit for all atoms these coefficients. You also need this damping function because you have to turn the interaction, the Vanderbulge interaction off when the charges start to overlap. Otherwise, you have a divergence at 0. It's not really first principle of first and a half, but it works quite nicely. This Grimme DFT plus D3 is the most accurate, and it works quite nicely. Otherwise, there are other further approaches that are seems to work quite well, in particular the called Tkachenko Schaeffler approach and the exchange Hall dipole model. And in these cases, instead of computing the charge, the coefficients of these coefficients here from a fixed table, and you compute those coefficients directly from the charge density with some method. So you do everything first principle, so to speak. Okay, I have been talking too much, so I'm way behind. Just a quick description of a quick introduction on how you actually solve those equations, because until now I have been talking about DFT and results, and never saying how you get those results. Of course, it's a rather complex procedure that involves some numerical calculation. So I have mentioned that the Kohn-Sham equations are self-consistent. So you have to solve for Kohn-Sham orbitals under a potential that depends upon the solution themselves. So you have to do some self-consistency. And this is one possibility. So you solve self-consistency, those equations, with the charge density that depends upon the Kohn-Sham orbitals, and ensuring orthonormality constraints. But this comes out almost automatically. There's also another approach, actually, which is quite sometimes more convenient, sometimes less, but it's basically equivalent. That is, you can say, okay, I have an energy as a function of Kohn-Sham orbitals. Those Kohn-Sham orbitals have to be orthonormal, actually. So this is a constraint I have to impose. But in the end, this is sort of a problem of minimization. So a problem of finding a minimum of a function, which is a quite well-known problem. And so the global minimization approach doesn't have Kohn-Sham equations, but it uses basically the same ingredients to minimize the orbit, to minimize the energy directly. It's the same because this also comes out from the minimization of the orbitals, of the energy. So here you are minimizing the energy by solving these equations, and here you are minimizing the energy by directly minimizing the energy. So it's quite the same. It's quite the same, and in the end, the minimization of the energy of a function, mathematically, it's much simpler if you know the gradients. Gradients with respect to what? In this case, the gradients with respect to Kohn-Sham orbitals. So the variables are the Kohn-Sham orbitals. So you need this quantity, basically. You need the functional derivative with respect to the Kohn-Sham orbitals. And this is nothing but the Hamiltonian, the Kohn-Sham Hamiltonian times a Kohn-Sham orbital, minus a term that comes from, that ensures orthonormality. This term, once you diagonalize it, yields at the ground at self-consistency at the end, yields the Kohn-Sham eigenvalues. I'm afraid that I have to stop here. Any questions? Yes?
You say that idea.
It's something that has been observed. I'm not aware of any case in which LDA doesn't overbind. I'm not sure if we can find a better justification than this. Okay?
This is yours.
Ah, no, un pochettino. Questo fa guardare. Perché mi sto incasinando. Pensavo che fosse ci sei tu
Okay, is it working? Okay. Yeah, so about LDA versus GGA, I don't know, one thing that people say is that LDA is correct in principle for a uniform system, and then you expect it to be more wrong for inhomogeneous systems, so the atom is the most inhomogeneous system, so one justification that is, just a way to is a posteriori, so, no one understood before, but